Okay, let's dive right in. This is Chapter 6, Applications of Integration Overview. So this is the first chapter we're covering here in Calc 2. Our objective in this video is to introduce the chapter content and objectives. Chapter 6 is not a very long chapter, and it builds on Chapter 5 in that we are still talking about integration. So we're going to be doing quite a bit with integrals. And here we're going to talk about some preliminary applications of what an integral does. And to help motivate that, I have here a diagram, a sketch of a cross-section of a blood vessel. Okay, so imagine that there's blood. Here's little blood vessels running through here, or the little blood cells, right? And through the length of this vessel, okay, and the vessel has a length L, curly L, okay, and we assume that the vessel has a radius, capital R, and at some point inside the blood vessel, right, for instance, right here, okay, it's some distance little r from the middle of that the blood vessel, right? So if you can think of this cross section as basically being circular, right? This little r is how far away you are from the center there, okay? And so in this particular example that we're going to talk about in much more detail in a later part of the chapter, okay? The velocity of the blood at that point is given by v as a function of little r being capital P over 4 nu L times capital R squared minus little r squared, okay? So P here, capital P, is what we call the pressure differential between the ends of the blood vessel. Okay, so the difference in blood pressure from one end to the other. Nu, this Greek letter, is the viscosity of blood. Both of these are going to be assumed to be constants. Okay, L we already talked about, it's the length, and capital R is the radius of the blood vessel. Okay, so the only thing here that's changing is R. So as a function of little r, okay, and at any given point it's given by this. But our question here is, what is the average velocity, VAVG, over the entire cross section? So the average over the entire cross section, this circular area, right? We will find, okay, that our target here is we want, so for little r being between 0, so 0 being the dead middle of the blood vessel, and capital R being the wall of the blood vessel, okay, we know that it'll range between V of 0, so if you just plug in 0, right, you get P capital R squared over 4 nu L, and V of capital R squared minus R squared is 0, so you just get 0. So the velocity, and this makes sense, the velocity of any blood cells along the wall of the blood vessel is 0, so it's not moving. But in the middle, we suspect it's maximized, okay? So the average velocity, though, we're going to figure out a technique to determine this using integration. We will find that. So our little glance ahead here. We'll find that the average velocity is going to be 1 over r, the integral from 0 to capital R of the velocity, p, 4 over 4 nu L times r squared minus little r squared dr, d little r, right? So we're going to see this in section 6.5, average value of a function. Why do we integrate? How does this connect to average? We'll see in time that integration is a tool for adding up infinitely thin anything, okay? So the key insight here will be that we're taking infinitesimally thin things, so adding up infinitesimally small things. We can convert this into an integral describing the infinitesimally thin things. And be able to describe things like area and volume and, yes, average value, okay? So for the full learning objectives, okay, you want to see the Canvas page for the module. And as we move through this chapter, we're going to be talking first about area between two curves.